Okay, folks, this is our final video of today's lesson, and in it we're going to be talking about multiplying and dividing complex numbers in polar form. I'm going to talk you through the formulas, and then we're going to apply them by actually doing some calculations. But I feel like something that's easy to get lost in here is what is the big picture? What is the big idea? Because what we're going to do in this section, this is really the point of working with complex numbers in polar form. The fact that this is amazing is probably not going to sink in now, but it might sink in later when you look back at it. I'm not sure. Anyway, I'm telling you, this is amazing. Something magical happens when you convert two numbers into polar form and multiply them in polar form. And the cool thing that happens, I'm going to show you a formula for it in just a second, but I don't know if the formula really does justice to how cool and amazing this is. All right, if you have two numbers in polar form and we multiply them, to multiply complex numbers in polar form, here's what we do. We simply multiply the moduli, which is the moduluses. That's like the r's. And add the angles. Those are the thetas. So if you're multiplying two numbers and they're in polar form, if they're written in polar form, you know what the moduli are and the arguments, the angles are, and to get your new complex number, you simply multiply the moduli together, and then you add the angles, the arguments together, and that is the modulus and the argument of your new number. All right? It just works beautifully. It's amazing. When we divide numbers in polar form, it's quite similar. We divide the moduli, and we subtract the angles, the arguments. All right. This, in my mind, this is the intuition, this is the idea behind this whole section. And now the trouble is that actually carrying it out there's a lot of things to keep track of. We have two complex numbers. Each one has a r and a theta. There's the cosines and the sines running around, etc. So the formulas don't look neat and tidy, but the idea that they're capturing, which is when we multiply two numbers, we multiply moduli and add arguments. When we divide moduli and subtract arguments. That is the big idea. All right, let's go ahead and look at the formulas. So if we have two complex numbers in polar form, well, we're going to have a first complex number in polar form, and it's going to look like this right here. This is our first complex number in polar form. And it has a modulus R1, and it's times cosine of theta 1, that's our first angle, our first argument, plus I times sine of theta 1. That's our first complex number. Our second complex number is going to be similar, but it will have a different modulus, R2, and it will have a different angular argument, theta 2. And the question is, if we have these two guys multiplied, what do we get in the end? And we are not going to multiply out everything using FOIL and so on. We are simply going to use this formula, although it's worth noting that this formula can be proved using the angle addition and subtraction formulas that you saw back when we were studying trigonometry. All right, so the key thing to note is here, there's two formulas. There's a formula for addition, that's this one, and a formula for division. Sorry, there's a formula for multiplication, that's this one, and a formula for division, that's this one. The multiplication formula, what it starts by saying, it just looks like a mess, is one complex number in polar form times another complex number in polar form. And you'll see that this one is just exactly our first complex number in polar form. This one is our second complex number in polar form. And this is saying what happens when you multiply one complex number times another. Well, we're going to get a third new complex number in polar form. It is going to have a modulus, and that modulus, that number out in front, is going to be obtained by multiplying just r1 times r2 together. And then inside it's going to have cosine of angle plus I times sine of the angle, and that angle, the argument, is just obtained by adding up the two angles, the theta 1 and the theta 2, from our two numbers. So this says to multiply two complex numbers in polar form, simply multiply the moduli, add the arguments. All right, there's a similar formula for division. For division, we have our two complex numbers. The first one here is on top of a fraction, the second one's on the bottom of a fraction, and we would like to divide and then get an answer in polar form. So it should have, the answer should have a modulus, an r in the front, and that r is obtained by just dividing r1 divided by r2. And then it should have an argument, an angle, and that angle is just obtained by subtracting. You do theta 1, the angle from the top of the fraction, minus theta 2, the angle from the bottom of the fraction. Okay, that's the formulas that just apply this idea, and now let's actually see how it works. So this is example 21.10, A, B, C, and D, and then I'll do a final intuitive bonus, and then we'll be done for today. Okay. Let's take a look. Part A. Oops. Change back to black. Get rid of that guy. Here we go. Part A. Well, this is 5 times cosine of 11 degrees, so we're working in degrees in this problem, plus I times sine of 11 degrees. That's our first complex number in polar form. It has modulus 5 and argument 11 degrees, times our second number in complex number in polar form is 8, that's our modulus, and then we have cosine of 34 degrees plus I sine of 34 degrees. Great. And what do we do? Well, what is this going to be equal to? Since we're multiplying two complex numbers, we want to get a new complex number, and we want that new complex number to be in the form r times cosine theta plus I sine theta. That's our polar form that we're after. And the formulas above tell us how to find that polar form. They say the r, the number in the front, will just be obtained by multiplying 5 times 8. That gets you 40. And then inside the angle theta, it's going to be cosine of that angle plus I times sine of that angle. That angle is obtained by just adding the two angles, 11 degrees and 34 degrees. So 11 plus 34, that is 45. So this is cosine of 45 degrees plus I times sine of 45 degrees. All right, what do we do next? Nothing. We are done. This is the complex number that we get as a result of multiplying the two complex numbers above. And you'll notice it required very, very little calculation. That's part of what is amazing about these. The formulas look a little daunting, but in practice, they actually make these calculations, these computations, quite simple. Okay, pause. Go ahead and work on parts B, C, D, and E, and then come on back and we'll do them together. Here we go. Okay, so part B, I'm going to go ahead and this one I think that I can still read. So this is our second multiplication problem. This one is similar, but I see looking ahead that the angle is given in radians instead of degrees. We're going to see how we handle that. And there's a hint here, which is that you handle it in the same way you did before. So this is 3 times cosine of 5 pi over 8 plus I times sine of 5 pi over 8. That is our first complex number, times 12 times cosine of 7 pi over 8 plus I times sine of 7 pi over 8. And remember, we want to write our answer in polar form. So to do that, we need to find r and we need to find theta of the answer. So how do we do it? Well, the r is just going to be 3 times 12, which is 36. Theta is going to be, well, we add the two angles. So we add the angle here, 5 pi over 8, and the angle here, 7 pi over 8. So this is 5 pi over 8 plus 7 pi over 8. They're both over 8, which is nice. We can combine them into a single fraction and add the tops together. 5 pi and 7 pi gets you 12 pi over 8. Very nice. We can also simplify this. We can cancel 4 out of the top and bottom. And if we do that, then let's see, 4 goes into there 3 times, into there 2 times. This is equal to 3 pi over 2. So we found our r, we found our theta. We can just plug those in to get our the result of doing this multiplication. Here we go. My next step is equals. What is it equal to? Well, it's 36 times cosine 3 pi over 2 plus I times sine 3 pi over 2. And that's our answer to part B. Okay, let's go ahead and take a look at C. Oh, it seems I've missed a part of the instructions here, which say write your answer in polar and standard form. So although the calculations we've done in A and B are correct so far, they're both given, the answers are both given in polar form, and we also need to write them in standard form. So in standard form for part A, we're just going to take the polar form, replace cosine 45 and sine 45 with what they are equal to. That's one that you should know in your heads. Cosine and sine of 45 are both equal to radical 2 over 2. So for standard form of this, we get the 40 stays out there. That's the modulus. And cosine of 45 is radical 2 over 2 plus I times sine of 45 radical 2 over 2. And then we just simply multiply that 40 through. When we multiply it by each of these fractions, it cancels with the 2 on the bottom and leaves behind 20 radical 2 plus I times 20 radical 2. Or if you want to put that I at the back, we can do that easily like that. So here is our part A in standard form. And then part B in standard form, let's see. The angle 3 pi over 2, we're going to need to find the cosine and sine of that. If you know those off the top of your head, then that's great. If you don't, it may help to think this is 0, this is pi over 2, this is pi, or 2 pi over 2, this is 3 pi over 2. This 3 pi over 2, this is the angle 270 degrees, or the angle that goes straight down. And I happen to know for that straight down angle, the cosine is 0 and the sine is -1. So we can substitute those values in. So here we have standard form is 36 times 0 plus I times -1. And the 0 plus that 0 just disappears, and the 36 we can multiply with the -1. That's -36i. That's what this thing looks like in standard form. Okay. With that in mind, with our carefully read additional instructions in mind, we're now going to do part C, and we'll give the answer in both forms. Let's go ahead and do it here. For this one, I'm just going to go ahead and copy it. So we have it here for reference. And on the bottom, those are 7 pi over 12. I cut them off a little bit in my sloppy copy. Here we go. Okay. So we're dividing two complex numbers. Here's the top one, here's the bottom one. There are the moduli, 32 and 8. Here are the arguments, the angles pi over 4 and 7 pi over 12. And we know from the discussion above that when we do this, the modulus of the resulting complex number will be 32 over 8. We just divide the moduli. And 32 over 8 goes in nicely. It's equal to 4, so r is 4. And the theta is going to be, well, it's the number, it's the angle from the top, or the argument from the top, pi over 4, minus the argument from the bottom, 7 pi over 12. To calculate this one, we're going to need a common denominator. That's going to be a denominator of 12, and so that first pi over 4 we're going to multiply on the top and bottom by 3. So we have 3 pi over 12 minus 7 pi over 12. Since they have a common denominator, we can subtract 3 pi minus 7 pi. This is negative 4 pi over 12. And the 4 cancels on the top and the bottom, and it leaves behind negative pi over 3. Now, this angle, negative pi over 3, let's just do a little thinking about where that angle lies. This is 0, and this is negative pi over 2. So negative pi over 3 is going to be somewhere like that, negative pi over 3. And that's the same as a negative 60 degrees. So if it helps you to think in degrees, that's negative 60. This is one of those angles where we should know the sine and the cosine of it, but we'll come back around to that later as a challenge to you. Think about what is the sine and cosine of this angle. All right. From this r and this theta, we can directly write down the solution. The solution to this division problem, I'll just write it up here. This is, to make it really clear, this is equal to, well, what is it equal to? It's equal to 4 times cosine of negative pi over 3 plus I times sine of negative pi over 3. And we'll just pop those into parentheses to make sure everything's nice and tidy. This is our answer in polar coordinates. And then to convert it into standard coordinates, or to standard form, we just need to know what the cosine and the sine of that negative pi over 3 are. So this is the way that I think about it. I always like to draw that vertical line. That gives me a right triangle. Here's my angle. The reference angle there, the angle inside there is, think of it as a pi over 3. But since we're in the fourth quadrant down here, sine, let me see, is going to be negative. Cosine is going to be positive. Now the angle pi over 3, cosine pi over 3, sine pi over 3, cosine of pi over 3, cosine and sine. This is one of the ones that goes in the pair, radical 3 over 2 and a half. And it's the one where the sine is the larger. So this cosine of pi over 3 is a half. Sine of pi over 3 is radical 3 over 2. And when we move into the fourth quadrant, when we look at cosine and sine of negative pi over 3, since we're in the fourth quadrant, the cosine is still positive, it's 1/2, and the sine is now negative. It's negative radical 3 over 2. That's because it's in quadrant 3, where cosine is positive, sine is negative. All right, so we have the cosine and the sine of our angle. So to convert this into standard form, we are just going to substitute those into our polar form. So standard form is going to be 4 times cosine of negative pi over 3 is 1/2 plus I times sine of negative pi over 3 is negative radical 3 over 2. Now this one we can simplify a little bit. We're going to multiply the 4 through here, and when we multiply the 4 through, things cancel. We just get 2 plus, I think that's not going to be a plus. Let me see. The 4 is going to cancel with this 2 on the bottom and leave behind a 2, but also times a negative radical 3. So I guess that gives us negative 2 radical 3 times I. And there is our complex number, the result of doing that division, here in standard form. So we have standard form here, polar form here. Those answers are equal to each other. They're just written slightly differently, and both of them are equal to what you get when you divide this complex number by this one. Okay, so let's look at D. Here we'll once again go ahead and grab it. And for this one, well, I noticed, first of all, that they are working in degrees rather than in radians. And we have a complex number on the top with a modulus of 4 and an argument of 203 degrees. And on the bottom, we're dividing by the complex number with modulus 6 and argument 74 degrees. So what do? Just as before, we find r. R is equal to 4 over 6, which is 2/3. And what is our angle theta? Well, since we're dividing, we're going to go 203 minus 74. Okay. 203 minus 74 is, let me see, 129 degrees, if my mental arithmetic is good. Although it is, I admit, 1 in the morning, so it's worth checking. So our R, our modulus is 2/3, and our angle is 129 degrees. Let's go ahead and write this in polar form. In polar form, this is 2/3 times, oops, ooh, it gave me a fancy circle. I didn't intend that. Here we go. Times cosine 129 degrees minus I times sine of 129 degrees. So this is our answer in polar form. And then to convert to standard form, we're going to need to find the cosine and the sine of 129 degrees. You can do this in your calculator, the key thing to watch out for is that these are numbers in degrees, so make sure that your calculator is set to degree mode before plugging those numbers in, or you're going to get something very bizarre. When I plug them into my calculator, I get cosine of 129 degrees is equal to... Oh, I don't have it handy, so let me see. We'll have to look it up. So I have a cosine and a sine here. I'm just going to delete out the numbers and put in the one I want. This is 129 sine 129. Okay, cosine of 129 is negative 0.629. Cosine 129 is equal to negative 0.629. And sine 129 is equal to 0.777. So, converting this into standard form, we still have that 2/3, and then inside cosine of 129 is negative 0.629 plus I times 0.777. And now what do we need to do? We need to multiply through by that 2/3. And here I'm going to do that to the side. 2/3 times negative 0.629 is negative 0.420. And similarly, 2/3 times 0.777 is 0.518. And don't forget, we still have that I in there. Excellent. So when you divide this complex number, 4 times cosine 203 degrees plus I sine 203 degrees, by this one, 6 cosine 74 degrees plus I sine 74 degrees, the result is this complex number. You can write it either this way in polar coordinates or this way in standard coordinates. Okay, that's part D. Now, we're basically done with the example. I just want to do one more brief discussion. This is the intuitive bonus, I called it. Without doing any calculation or conversion, describe where in the complex plane to find the number obtained by multiplying these two numbers together. So we'll just get ourselves a little clear space to work in here. This is not going to take a lot of effort. But what it does do is I just want to illustrate for you when I work in the complex numbers and I have to think about multiplying or dividing complex numbers, I use the ideas from polar coordinates to help me understand what's going on, even if the numbers are not in polar coordinates themselves. So let's go ahead and take a look at this. If we draw the complex plane and we plot these 2 points, so let's see, 5 plus 2i, 1, 2, 3, 4, 5, plus 2i, that's this guy right here. I'll make that bigger. And then minus 1 plus 6i, minus 1, and then we're going to need to move this out of the way because I didn't plan ahead. 1, 2, 3, 4, 5, 6. That's right here. Okay, these are our 2 complex numbers. And when we multiply them, it's not totally clear what the heck we're going to get. We could, of course, multiply them out using FOIL, and we would see where the answer is. But I can give you an idea of where that answer is going to be just by looking at this picture. So, if we draw in our usual lines connecting the origin 0, 0 out to our complex points, I just want to look at 2 aspects of these lines. The first one, because in the end, we're going to get a point somewhere in the complex plane, and where does that point end up? Well, first of all, how far away from the origin is it going to be? I can tell you, it's going to be this distance times this distance. Now, I could do a little calculation and get this distance, but this is a distance over of 5 and up of 2. So in particular, this is a distance that is positive, of course, and bigger than 1. Indeed, it's also bigger than 5. So this is something it's a distance bigger than 5, probably less than 10, just by estimating. And this one here, similarly, this distance is bigger than 6. So something a little bigger than 5, bigger than 6. This is going to be a distance. R is going to be bigger than 5 times 6. It's going to be bigger than 30 at least. So if you want to know where this thing is going to be, it's going to be kind of far away from the origin. If this is a distance of a little more than 5, a little more than 6, this is going to be a distance of 30 off in some direction. It won't be able to graph it even on this picture because I haven't made the picture big enough. So that's sort of informative. And then the other part is about the angle. So let's just look. This angle is in the first quadrant, and this angle is in the second quadrant. And if you were to take these 2 angles and add them together, when you add angles, it's almost like you take a copy of this angle and you go to this angle and stick a copy of the first angle on there afterwards. In fact, let me do the first angle in green. And then let's imagine that we copy that angle over to the end of angle 2. So this angle I'm drawing now, this angle is the first angle plus the second angle. Here's the second angle, and then added onto it is the first angle, and so the whole thing is the first angle plus the second angle. And what I can tell you is this is the direction that this thing goes. In particular, it's going to be in the second quadrant. So, where is this located? If we were to multiply this out, where is this located? It's located in the second quadrant, and it's located away off this direction, a distance of about 30, maybe a little more. Yeah. So if you want to have some general feeling for where these 2 things would end up, that's where they would go. If I were looking for this, if I were to plot it, if I were to multiply it out, find the actual coordinates, you would find that it was in the second quadrant, pretty far away from the origin, off in the upper left direction. Okay, that's what I mean by the intuition. When we look at these 2 points and we think about where are they going to go when we multiply them. Complex multiplication means we're just going to take the angle of this one and the angle of this one and add them together. That's going to get us an angle over here. And the length of this one and the length of this one and multiply them, and that's going to get us a length that goes way off the board here. All right, that's it. That's the end of our final example. Go ahead and give the WebWork problems a try, and please let me know if you have any questions. Thanks.